At it fundamentally is the idea, the concept that the fundamental building blocks of nature are not point particles but are extended objects, loops or strings, and from that follows a very rich sort of mathematical structure, and in particular describing gravity. And so string theory has provided us with one of the candidates, perhaps the best candidate for a quantum theory of gravity.
Just as the different vibrational modes of guitar strings correspond to different musical notes, so different vibrational modes of fundamental strings give rise to both matter and force-carrying particles. In particular, a closed string was shown to have properties of the long sought-after graviton, and this implies string theory can explain all particles and forces, unifying quantum theory with general relativity.
So what we believe is that if you take a theory of quantum gravity, then you would be able to have some new kind of effects like discretization of your space-time, and you might therefore be able to understand what happens at what we call it as a Big Bang.
I was looking into phenomena related to the strong interactions, to the nuclear force. I arrived at an equation, at a formula, which was supposed to describe, these interactions or these processes. It was only a few years later that formula was understood as describing the collision of strings. After it was realized that indeed there was a string behind these mathematical models, the theory was abandoned as such because it didn't quite work in the details. So between 74 and 84, very, very few people were working on this theory until the work of Green and Schwartz proved that this could be a consistent theory for a bigger scope, which was the description of gravity and its quantization. In fact, as a description of all the interactions, including the strong interactions. The problem that the new incarnation of string theory is supposed to solve is to reconcile or allow to put together the theory of gravity given by general relativity and the quantum mechanics. Quantum effects give infinities which go out of control. Now, the beauty of string theory is that not only it reconciles quantum mechanics and gravity, but it eliminates completely these infinities. String theory comes with its extra dimensions of space. So, in order to reconcile this with our perception of a 3 + 1 dimensional world, okay, 3-dimensional space and one time, we have to imagine, although there are alternatives, the simplest one is to imagine that these extra dimensions are small and compact. Okay, for instance, think of a little circle. Okay, now T-duality tells us that strings behave very strangely in the presence of compact dimensions, in the sense that they cannot distinguish between a certain compactification radius and a dual one. That's why it's called duality, which is small. If the original circle was large, then the dual circle will be small, and vice versa. In cosmology, there is a quantity called the scale factor of the universe, which tells you how distances, for instance, of clusters of galaxies, change in time.
The scale factor is a key cosmological parameter which represents the expansion of the universe and increases with time. The classical Big Bang, the scale factor is 0, and values such as temperature, density, pressure, and curvature become infinite. The expansion or the evolution of the universe can no longer be extended back in time, and so the Big Bang singularity becomes the absolute beginning. So what happens to the scale factor in string theory?
There is a duality similar to the one related to the compactification radius for the scale factor. In other words, the equations of string cosmology, as opposed to Einstein's cosmology, have this extra symmetry in which you can replace the scale factor by its inverse. There is another symmetry that this time string cosmology and Einstein cosmology share, which is the inversion of time. Okay, we know that we can run the expansion of the universe backward and we find a contracting universe solution to the same equations. And now if you combine these two symmetries, scale factor duality and time reversal, you get a new cosmology which looks very interesting because it looks as if it wants to describe a universe before the Big Bang. The idea of this scale factor duality based cosmology is that there had been an evolution of the universe which was some kind of mirror image of what happened afterwards. So in the same way as the post-Big Bang era where we live, in our model will last forever, and I think it also lasts forever in ordinary inflation, okay? For us, because of this symmetry, this duality, also the past is infinite, okay? The future and the past are both infinitely long. And the behavior of the scale factor is of the inflationary type. So it seems, and this was the thing which thrilled me in the early 90s, that naturally it seems that string theory leads, thanks to this duality, to some inflationary cosmology.
The starting point for the ekpyrotic model was to think of the Big Bang occurring as a collision, as a collision between our universe and really another universe in a higher dimensional space. So a very dramatic sort of framework to think of this. But it was inspired by the idea of brains in string theory, and brains are these extended objects, not now just strings, not just loops of matter, but planes or hyperplanes in higher dimensional space. Neil Turok, Paul Steinhardt, Bert Overath and collaborators took this seriously as a model for the Big Bang, that you would really have the Big Bang would be a collision in between brains, and that collision would heat our universe and indeed imprint the structure in our universe would originate from the collision of these brains. And so that's a very fascinating idea, and they studied the spectrum of perturbations that would happen. But again, you have this issue of a singularity. The hope was that in the high dimensional theory, you would be able to resolve what would just be an apparent singularity. And so the challenge is to do the calculation of the singularity in some fundamentally richer theory of gravity that might come from the string theory setting, but that's very, very difficult and very controversial as to how to do that calculation.
One possibility to do this has been to mix the string-inspired ekpyrotic model with loop quantum cosmology, which is thought by some to remove the singularity.
String gas cosmology is based on the physics of closed strings, and closed strings are responsible for gravity, unlike open strings. In standard cosmology, which is based on general theory of relativity, if you go backward in time, the universe shrinks and becomes smaller and smaller until it hits the so-called singularity point. The curvature of space-time becomes infinite. The pressure becomes infinite. So there are so many infinities in this system, while the volume or the size of the universe is zero. It's nothing. So in this string gas cosmology, which is based on the notion of replacing a point particle, which is completely a localized notion in physics, by some extended object like a string, will buy you a few things. One of them would be the so-called T-duality, some kind of symmetry between the physics of large stuff and the physics of small stuff. So this symmetry between these two things will give you a cosmology which would be the cosmology of the expanding universe, would be the cosmology of the contracting universe. And these two universes will be connected through what is known as the self-dual point. The cosmology of expanding universe would be the same as the cosmology of contracting universe. And since these two should exist side by side together in order to preserve this T-duality, you would not hit any singularity, because now the smallest size of the universe would be the size of a string. So the universe at most can be shrunk to the size of a string, and that's the point we call it the self-dual point. Strings are winding around space. Now our space should be compact, and therefore we use a torus. So strings are winding around a torus shape. What happens, these winding modes are changing to so-called momentum modes. The strings are unwound, then that's the end of the stringy phase, or as you want to call it, the Hagedorn phase. So what happens is that how we describe the production of this gravitational waves. There would be some, this you can assume is just like having a bulge on your torus, on your tire, okay? And then this bulge caused by the fluctuations on the winding modes of strings. And then this bulge rotates and propagates along the space, which in this case space is like a torus. Unwinding the strings will give you the expansion of the universe.
The model says then the following: our universe starts with extra dimensions because string theory needs extra dimensions. If you take superstring theory, there are 9 plus 1 dimension. If you take branes, there are M theory 10 plus 1 dimension. So let's start with a universe which is very small and is made out of 9 or 10, you name it, special dimensions. And the universe starts expanding. Now, if it starts expanding, you have some modes, which they're called winding modes, which they have an energy which is proportional to the length of your torus. Let's take that. So then at some point it becomes energetically too expensive to keep expanding. And the universe is going to start contracting. So as you go to smaller and smaller spaces, they become energetically very expensive. So the universe is going to go back and forth. So this was a way of explaining the initial singularity, because you're never going to reach the zero because it becomes too expensive. It was a way to solve the issue of dimensionality of space-time, saying that at some point the universe goes through these oscillations, so the universe is old, the entropy of the universe is big, but something happens, that a random kind of event, and now 3 out of these 9 or 10 dimensions, they become bigger, they compactify themselves. And in the theory, in string theory, each string, as it moves, is one-dimensional object. It moves in space-time, so it spans a 2-dimensional kind of brane, a 2-dimensional worksheet. So only if you have 2 plus 2 equal to 4, only 4 dimensions, you can have 2 strings that are going their worksheet hit to each other and unwind, and that's what you want in order to liberate the universe.
Cosmic inflation works in any number of dimensions, and you can get still scale invariance in any number of dimensions, which is not the case here in string gas cosmology. You can see it nicely that it only works in 3 spatial dimensions. And this is the feature of working with the strings, because the strings are extended objects.
There are 2 possible definitions of the Big Bang. One is that it's the initial, is the beginning of time, is a singularity beyond which you cannot go, and so on and so forth. And the other, which is really what is related to observations, The first is a theoretical concept. The second, which is really related to observation, is that the universe had to be hot, very hot at some moment. And in the standard inflationary scenario, that moment comes after inflation, not before inflation. It comes after inflation, because inflation, by its exponential growth of the universe, cools it down practically to zero temperature. It has to reheat the universe to a sufficiently high temperature so that certain processes take place, like Big Bang nucleosynthesis producing helium, and things like this. It cannot happen at low temperature. So, what I like to say is that the standard model of inflation is a pre-Big Bang model, because we shouldn't talk about just hypothetical singularities, which I maintain they are really obtained by using general relativity beyond its limits of applicability. The expansion rate of the universe was almost constant during inflation, which means that the expansion was exponential. In our model, it is not constant, this expansion rate. Actually, it grows in time. So this leads to different predictions.
And your inflationary, while it goes at a different rate, your expansion rate
Yeah.
is different, it still ends up with these same factors, flat and...
Flatness, yes, but okay, what it does not give automatically is a scale invariant spectrum of perturbations. In fact, for some time it looked that it could not give at all a flat spectrum of perturbations. For other reasons, people found a mechanism called the curvature mechanism, to which British scientists contributed a lot, by the way, once himself, I think. And through that mechanism, we found that actually string cosmology can give a flat spectrum, a nearly scale invariant spectrum.
We have been able to show that the most interesting and profound feature of cosmic inflation, which was explaining the fluctuations in the universe, the correct prediction of existence of mass fluctuations in the universe, we are able to also to predict that. But in our model, we have to admit that we are working with the case that the universe started to being flat and remains flat. Well, inflation does a fantastic job to explain this. And there is ample of time here during this hackathon phase. You have ample of time to get rid of the magnetic monopoles, and therefore I'm totally agree with Paul Steinhardt's recent paper that he's claiming actually you just need to have more time to get rid of these things.
Many string theorists believe that there's a huge landscape of solutions to string theory, which are populated by a multiverse thought to be generated by eternal inflation. Can the pre-Big Bang model also generate a multiverse?
The initial conditions look like a chaotic sea of waves, gravitational waves, scalar waves, if you want also electromagnetic waves and so on. Now these waves would collide, interact, and as the strength of the interactions grew, because this was the solution, eventually they could collapse gravitationally, and so by forming black holes in this agitated sea, okay, and each black hole would correspond eventually to a separate universe, or if you want, the inside of a black hole is a cosmology.
The idea that a universe can be born from a black hole is most associated with loop theorist Lee Smolin. However, there is no consensus in the loop community regarding this view. Similarly, it may not be the consensus position in the string community, but there have been well-respected string theorists arguing this is a reality, and the latest edition of Scientific American has a new incarnation of the idea on the front cover.
The distribution of galaxies on the largest scales in our universe reflects the dynamics at even earlier times. And models like inflation, like the pre-Big Bang, like the ekpyrotic model, the way we test those, I think the best way we have currently to test those is through the predictions they make for the distribution of matter on large scales in our universe. So one way to do it is to these very large scale surveys, high redshift surveys of galaxies in the universe today. So my colleagues here in the University of Portsmouth, they are experts in surveys of galaxies at high redshift. Today in the universe we see a faint background radiation, the cosmic microwave background radiation, and we've got a picture of the sort of patterns you can see here in that. This is from the NASA's WMAP satellite, and at a very small level, at just 1 part in 100,000, you begin to see fluctuations in the temperature, and those are fluctuations in the temperature of the Big Bang. And we believe these fluctuations originated as quantum fluctuations at even earlier times. So we study the statistics of these fluctuations. It reflects density fluctuations, and it also has the possibility of reflecting not just the density field, but also the gravitational field in general, and in particular that would include gravitational waves. Inflation or the pre-Big Bang make distinctive predictions for the spectrum of these gravitational waves. So the pre-Big Bang or the ekpyrotic models do produce gravitational waves, primordial gravitational waves during these pre-Big Bang phases. But because you're running towards a singularity, the amplitude of the gravitational metric fluctuations, the gravitational waves, are growing and growing as the evolution progresses. So that corresponds to smaller and smaller cosmological scales. So that means that on most of the gravitational waves are produced on a small scale. There's very little left on the large scales. There's a very low amplitude on the large scales. So it's hard to produce a significant cosmological background on the very large cosmological scales that are being probed by the BICEP experiment. So that would be a real challenge for these pre-Big Bang models, I think. So the string gas cosmology claims to be able to produce an almost scale invariant spectrum, but do make the prediction that nonetheless it should still have a slight rise towards smaller scales, and that's a distinctive prediction from inflation, where all the inflationary models have a decreasing energy density as the universe expands, and so they end up with a spectrum that decreases towards smaller scales. That's called a red tilt, because red has a long wavelength.
Okay, so any good, I would say, scientific theory should be falsifiable. So the analogy that I want to make here is just like having an analog radio and just turning your radio knob to higher or lower frequencies. So red tilt means if you go to a lower frequency, you should hear more noises. What inflation and V predict for fluctuations in energy is you will hear a little bit noises if you go towards longer wavelengths and shorter frequencies. So in that sense, there is no difference between our model and cosmic inflation, or I guess any alternative models. And that has been tested. If you get any model which predicts that there are some dependence on the scales, you are already out. There is no room for you to play. But the key feature, I guess, in our model or any other alternative models is what do you predict for the tensor fluctuations? Well, tensor means fluctuations in the fabric of space due to the gravitational waves. Cosmic inflation predicts that the same thing about fluctuations in energy is true for gravitational waves. Namely, the gravitational waves also would be scale invariant, and at best would have a tilt, like a red tilt, which was true for fluctuations in energy. So why our string gas cosmology model is kind of unique among any other string-inspired models like the ekpyrotic model or the pre-Big Bang cosmology is that we predict that not only the gravitational waves are produced at the beginning of the universe, we predict a blue tilt, which is unique to this model.
In order to test the theory, you simplify your initial model. And one has to be very cautious because you don't know at the end of the story the predictions that you found, how related are with the original model you had at the beginning. So for instance, if you were going to find that there is no observation of any kind of tensor polarization, and if there is no observation of relic gravitons, that would be a positive thing for a ekpyrotic universe. If you were going to find instead that there is no observation of the tensor polarization, but there is observation of the relic gravitons, that would be very good for the case of the pre-Big Bang model. In the standard inflation, we have the opposite of that. We have observation of the tensor polarization and non-observation of any kind of relic gravitons.
In March 2014, BICEP-2, an experiment at the South Pole observing the cosmic results mean if they are confirmed?
Certainly the simplest pre-Big Bang model that we constructed would be incompatible with the observation of gravitational waves from inflation, so with BICEP's result. Now, of course, as every theory, we are looking whether we can modify or extend the model or play with some free parameters we had in order to see whether we can get such a spectrum of tensor perturbations. But okay, it's not the most natural thing in any case.
But if we think they are right, so the good news is both inflation and our model predicts the existence of the gravitational waves. But the second thing, which still is an open question, and if you look at the raw data by them, it somehow prefers a blue tilt over the red tilt. Of course, the BICEP-2 didn't say anything about the tilt of the power spectrum, and I think still they didn't have that precision. Saying that we found the primordial gravitational waves, to my mind, is not enough to say that the cosmic inflation, is the winner of this race between these different models. What we are saying is that look for the tilt. It's great to find the primordial gravitational waves, but look for the tilt.
The BICEP-2 claims will be bad news for both the pre-Big Bang model and the ekpyrotic model, but good news for string gas cosmology. But the question remains, will the results hold up?
So it's a remarkable claim, and has been said, extraordinary claims require extraordinary evidence, and that's fair enough. That it's going to require a lot of examination. In particular, the questions that have been raised are whether this signal which they saw could be due to polarization of dust, foreground contamination, so it could be dust in our galaxy. So it turns out the best information may well come from the Planck satellite. It makes an all-sky survey, and so as well as mapping the cosmos at the edge of the universe, it's also mapping our galaxy. And so they've got many all-sky coverage, many frequencies. They should improve the models precisely of these dust foregrounds. And so we're now all waiting to see what comes out from the next release from the Planck collaboration.
So I believe that dedicated polarization experiments which are going on, in addition with extra analysis from the BICEP group, and also with the Planck data, which are supposed to give us some new results, I believe, by the beginning of by next fall, then we would be able in a more confident way to see if these results are correct.
It's not necessarily going to be easy, but if the amplitude is as large as the BICEP experiment reports, then it should be possible and what we've got to do is to test that gravitational wave spectrum across a range of scales. So there are proposals for future satellite experiments which would give a more precise measurement of the gravitational wave spectrum on the microwave background sky. There are also, the other way to go after it would be to look for direct gravitational wave detection experiments. And so which probe at very different length scales, so they're potentially looking for primordial gravitational waves really on the scale of the solar system, for instance. So there are ambitious satellite proposals like the Big Bang Observatory or the DESICO experiment.
Many string-inspired cosmologies point to the same conclusion seen in loop quantum cosmology, that the universe bounced from a previous collapsing space-time. Another theory, Java-Lifshitz gravity, also seems to make the same prediction. Why do these different models converge on the same answer?
Any theory that has some kind of discrete space, then by definition there you don't hit the singularity, because you have this elementary volume that you are going to hit. So the fundamental element which we have in string theory is the string scale. So I don't know whether that could be an explanation of why all these models they somehow go to this bouncing solution when we arrive at a very small scale that can be string scale on the one hand, or can be the discretization of your space in kind of like causal dynamical triangulations or loop quantum gravity or whatever.
Well, I think they came after us, but indeed, we are in good company. So in loop quantum gravity, you only have the Planck scale, and I guess so the bounce has to occur when the curvature is of Planckian scale order. Whereas in string theory, there is this different, conceptually different scale, which is the string length scale. All of these things are related to the basic idea that you cannot trust the classical theory all the way to the singularity. Now, for us, what comes first are string corrections. For them are maybe different kind of quantum gravity corrections. Infinity in the future doesn't scare us, I think. Even religions always talk about a beginning, but not about an end. We know the theory in the infinite past, and we can even construct the general solution of the equations. So we don't see any problem to extend these solutions all the way to infinity. I'm saying the beginning of time is a myth, not in the sense that I can prove the opposite, but in the sense that I don't think you can prove that there was a beginning of time. Okay, it's a myth in that sense. It's true if you apply general relativity all the way till the singularity. But I think almost all physicists agree that before you reach the singularity, something must come in.
I don't know. I think it's not very satisfactory to have a model with a start. And certainly the classical hot Big Bang cosmology beginning in a singularity, that is a prediction of, if you follow the general relativity to its logical conclusion, there's a singularity there at the start. But I think most physicists look at that and think, well, that's just the theory telling us that the theory breaks down. A singularity is that the theory is broken down. I think there must be some consistent description of all parts of our universe. I find it very unlikely that there's an edge either in space, that we'd fall off the edge of space, or that we should fall off the edge of time in that way back at the beginning of time. So I would think that there is a continuation, a smooth description. Whether or not that means time is infinite is another question, because we know that space doesn't have to be infinite. You know, you can have, here's a nice spatial surface which is more or less smooth and finite, but it doesn't have an edge. And so, we could have some smooth topology for space-time in that way, or it could be smooth and extends forever. And we may never know the answer to that question. I'm sure we will keep trying to push back further and further to learn more about the early universe and what happened before the early universe. We see these funny hot and cold spots, red and blue blotches on the sphere of the cosmic microwave background. As a singularity, you've got no physical description for why some places are hotter and some places are colder, and yet overall it's almost uniform. And all these pre-Big Bang models are trying to give us a theory in which we can make that calculation.
I think that is an open question. I mean, there is this, work by various people like Vilenkin, as you said before, who studied the possibility that the universe could not have a beginning, and he studied 3 different cases of universe. I mean, of scenarios. He took eternal inflation, because we know that inflation is eternal in the future. So the question is it eternal in the past? Now, then he studied the cyclic model. The entropy increases. The only thing that you can allow that to happen if the volume increases, so the energy density which we measure remains constant. But if the energy density remains constant, then we know that the average expansion rate is positive. And if that is the case, then we know that this theory, there is a theorem that says that this kind of theories that have that, they are geodesically incomplete in the past, which means that they cannot go to the past infinity, so they have a kind of beginning. And that's not the case that these theories try to say, that you don't have this beginning. So this is a problem, and I don't know how this could be resolved. Nevertheless, given that we do not know the full theory of quantum gravity, I don't think that we can definitely say this is right or this is wrong. And then he studied an emergent scenario, which I believe is called the cosmic egg as well, that you start with a universe which is static, and then something happens and the thing is going to start expanding. So for the 3 cases, he has shown that you cannot avoid the initial, the beginning. You might say that all these questions have been addressed not in the context of a full quantum gravity theory. And it might be that everything we know might change if you go to a full quantum gravity theory.
I guess, at least in the framework of string theory, whether you believe in the pre-Big Bang cosmology, whether you believe in the ekpyrotic universe or a string gas cosmology, there was no beginning for the universe. I'm sure there was something, whether you are passing through the self-dual point or the collision of the 2 branes for the ekpyrotic universe, which mimic the so-called Big Bang. But to me, it is hard for me to comprehend it, let's say it this way, that there was nothing and then suddenly the universe came about. Recently, Alan Guth also saying that he thinks that there was no beginning for the universe. The universe was past eternal as well. So if I want to bet, I want to bet for a universe which had no clear-cut beginning.
There seems to be no clear agreement on whether the universe had a beginning. Cosmologists such as Vilenkin and Matani argue that there most likely was a beginning, whereas many quantum cosmologists side with Alan Guth, who's recently suggested that there may be no such beginning. So is there any possibility of actually settling this dispute with observations?
Realistically speaking, I don't see how the observations are going to give us any kind of fingerprint about that. I don't exclude, but up to what we have right now, I don't believe that they can give us. Any kind of data we have, we analyze them within a particular scheme of a theory. And if we do not have the full quantum gravity theory, I'm not sure how we can, what do we look for?
A number of problems have been associated with a collapsing universe, namely the instabilities associated with anisotropies and the increase of entropy. How can these be resolved?
The anisotropy is washed out during this, what we call the string phase, in which you avoid the singularity. That the entropy that you produce at the bounds saturates a certain bound on entropy, which is sometimes called the Hubble bound. It is not that of course, that the entropy decreases or does something strange. Is that the bound itself gets relaxed as the universe goes from the contracting phase to the expanding phase. It's not a surprise that the bound, in the contracting phase, the bound tends to become tougher and tougher until it gets saturated. But at that point, precisely around that point, you bounce. Once you bounce, you start to expand, and then the bounce relaxes, namely goes up. The entropy also goes up by the second law of thermodynamics, but not as much as the bound. So there is a lot of room for entropy. For instance, today the bound is huge relative to what we know is the entropy of the universe today. So I think it's a very interesting question, but I don't think it's as bad as, for instance, is presented in Penrose's book, that, you know, the entropy had to be particularly low at the bank.
While string theory, loop quantum gravity, and Hajova-Lifshitz gravity all have been used to inspire bouncing cosmologies and are probably the prime candidates for a theory of quantum gravity, Wikipedia currently lists more than a dozen other candidate theories. Can they be used to try and understand the early universe?
I don't think that these models, they are developed to an extent that they can answer this kind of question. Causal sets is a very nice and beautiful kind of scenario. Just takes, you know, the basic idea of causality, but I think that it's so minimalistic that it's very difficult to go beyond and make some kind of, you know, claims about the origin of the universe and things like that. I also, because in these models you don't take that much into account the matter, so I do not think that these models can make, at least at this stage, any kind of claim about the phase before the Big Bang or the phase of the Big Bang itself.
String theory has been widely cited as the best candidate for a unified theory of physics. But in recent years, there's been a backlash arguing that it cannot be experimentally tested. Now, in this